Welcome to this second day of webinar 1. Today, the topic is about the design analysis stage. So welcome to all the participants, wherever you are. Good morning, good afternoon, good evening, good night. I hope you will have a good time with us for the next 4 hours. So today's lecture or series of lectures, first will be that I will introduce the concepts and some methods and tools for process design analysis. Then, let's see if I... So then we had already discussed yesterday the process synthesis stage. So today we are in 1.2 and this is lecture 1. And after my lecture, Professor Mario Eden from Auburn University will give the lecture on design of process operations and equipment using the reverse design approach. Then I will briefly go through the process analysis methods and tools, ending with how to identify process hotspots and define targets for improvement. And then the final 1 hour, we will show how all these methods and tools can be used to solve problems. It's not only our software today, but also other software that will be seen. During at the end of each session, there will be enough time for question and answer. So if you put your questions on the chat box, then our local Thai team organizers will read them out at the time of the question answer. You can also raise your hand and then they will unmute you so that you can ask your question. And tomorrow, then based on what we have done today, we will see how, after we define targets for improvement, how we achieve those targets through process innovation stage. So in our 3-stage methodology, yesterday we had the synthesis stage, and from there we have a processing route. If the process already exists, we can skip the synthesis stage and we can go directly to the design stage because we have a processing route. And so we have done the synthesis. Now today we will see that because we have a processing route does not mean that we have all the information. In order to have all the information, we need to perform a rigorous process simulation. We have to do or fill out the design details. So this is the part where we have to make a lot of design decisions, how we make them, and what is the best way to make them, what is the reliable way to make them, is what this part is about. But making the design is not enough because that gives us the option for process simulation. And after we have the process simulation, we have most of the data we need for analysis in terms of cost, in terms of LCA, in terms of sustainability, in terms of safety. And based on that, we will identify where the process has problems, and then we will set targets for improvement. And then it means that if we are able to satisfy the targets for improvement, by definition, we have a better flow sheet, better process than before. And that is what we will see in the next stage tomorrow at the innovation stage. So again, let's try to summarize on the concepts related to design decisions and simulation models. So note that we used in the synthesis stage yesterday, and we will start with the synthesis with the simple design now. And this is related to use of simple models. And what you will see is that the simple model like mixer, reactor, stream calculator, stream splitter, divider, or purge, with these we can represent any, I would say, chemical process, biochemical process, food process, conventional, unconventional, as long as there is some mixing, some reaction, meaning that compounds that come in and go out are different. If there is no reaction, then compounds that come in go out, so we don't need a reactor. Then to separate the compounds that come in, we need the stream calculator or stream splitter. And then in order to divide streams, we need divider or purge. So with these 4 units models, we can represent almost any chemical or similar process. Note also that for this kind of simple mass balance, thermodynamic property models are not needed because the parameters are calculated from the data. So here is a simple representation of a process flow sheet. And this process flow sheet is actually a real process that is converting benzene and hydrogen, reacting benzene and hydrogen to make cyclohexane. So what you see is a mixer, followed by a reactor R1, followed by a distillation column to separate cyclohexane from the reactants, and then a purge divider, because we have inert methane coming in that has to go out, and then the recycling. So the blank spaces are where actually the other unit operations that does not affect the mass balance would be needed. There are some additional constraints that the hydrogen to benzene ratio has to be 12 and methane to hydrogen ratio has to be balanced for purge. Because if we reduce the purge, there will be too much methane. If we increase the purge, there will be too much hydrogen going out. So this is the simple model, and we want to solve this. Yesterday, we already saw in Professor Grossman's lecture and my lecture that these models are very simple. Simple mixer, reactor with stoichiometry and conversion, then stream calculator with separation factors, and divider with divide fractions. So, and once we have these equations, we need to find out how to solve it. So we collect all the model equations for our process. So as I said, it doesn't matter how complicated the flow sheet is, we will only need these 4 sets of models. So if we have 5 distillation columns, we need 5 sets of stream calculators like that. So we collect all the model equations, then we analyze the model because we want to solve the equations. And you will see that analysis of the incidence matrix of the model equations help us to identify the solution strategy as well as which variables to specify. And then we derive a solution strategy. So in the table here, you see that we have 6 equations, and the 6 equations is times the number of compounds, NC. So if there are 4 compounds, times 6 will be 24 equations that we want to solve. And then the number of variables is not 6 times NC, but it's n times NC. So we have it's not n times NC, sorry, the component flow rates are n times NC. The total number of variables is 11 times NC plus 1. So which means that 5 times NC plus 1 variables need to be specified. So which variables should they be? Obviously, they should be the 2 sets of input variables, feed 1 and feed 2, then the stoichiometric coefficient, then the conversion of the key component, and then the separation factors and the divide fraction. So that gives us 3 NC plus 1 equipment parameters plus 2 NC process variables. So we have satisfied the degree of freedom. And then the remaining variables, F3, F4, F5, F8, F9, and F10, 6 NC process variables, we will solve for the 6 NC equations. So up to now is fine. Then we can look at the incidence matrix. And in the incidence matrix, in the columns, we put the variables. In the rows, we put the equations, and if you see a star, it means this variable appears in this equation. And to the left of the red line, the variables are specified, and on the right of the vertical red line, those variables need to be calculated. And then you can see that it's a nice lower tridiagonal form, but at the top right-hand corner, F4 has a star in equation 2. So that is because we have a recycle. So which means that we can solve this set of equations simultaneously, or if we want to solve module per module, that is first mixer, then reactor, then a distillation column, and so on, then we have to start by assuming a value for F4, and then we can iterate. That is typically the tier stream and the convergence of the tier stream. Okay, so the incidence matrix helps us to find out exactly how we want to solve the set of equations, and and what should be the calculation procedure. So we have both options, the simultaneous solution approach, as well as the modular approach. So, and the top incidence matrix, you see the equations in terms of equation number, and below you see in terms of the unit operations. So now we know the equations we need to solve and how we want to solve it. We remember that we have to specify the variables, 5nc plus 1. So we specify the variables, 5nc plus 1, the reaction data, the separation data. If the separation is easy, we can say it's 1. If it is a solvent-based separation, we can also say it is 1. Otherwise, we can give a number. The purge fraction is, we start with small, and then the feed stream 1 and 2. So giving all these variables, we can solve the equations, and you see in the table below the set of equations. So now we have a mass balance. For all the streams in the flow sheet, we know the component flow rates of every stream. So based on this, we add the energy balance to the simple model. But to calculate the enthalpy for the energy balance, we need to know the temperature and the pressure. We need to know both temperature and pressure, because in order to calculate enthalpy, we need to know whether it's liquid or vapor or a combination. So that's where the thermodynamics comes in, because knowing the composition and fixing the pressure, we can calculate the temperature, or vice versa. We need to specify 2 of the 3 variables, that is the state, the temperature, the pressure. We usually do the pressure because from the reactor, the pressure is known, and then we can say that this is a saturated vapor or a saturated liquid. That will be the bubble point or dew point. So then, given the composition and the pressure, we can calculate the bubble point and dew point temperature. That will give us all the temperatures of all the streams, and knowing that, we can calculate the enthalpy, and knowing that, we can calculate all the stream compositions, temperature, pressure, and enthalpy. And after that, we can find out which unit operation needs energy, which unit operation gives up energy. And that will help us to do the design that you will see in the next lecture. So now, based on the information, we have put in the heat exchangers. So now you can see that after M1, we have, let's keep E1 first. Let's go to E2. We need a heat exchanger E2 to bring the system to the reaction temperature. And after the reactor, we have to remove the heat. And because we need to remove the heat and we need to preheat the reactor inlet, we combine these 2 heat exchangers into one. So that's already integrated. but E1 is not able to heat to the temperature we need for reactor and not remove all the heat that is necessary to get to the feed state for the distillation. So we need two heat exchangers extra, that is E2 and E3. Then we do the distillation, we have the vapor product, we purge some of it because all the methane coming in has to go out, and then the recycled stream containing hydrogen and methane needs to increase the pressure to come to the reactor pressure, and then we have to send it back. So what you see is that we did not include E1, E2, E3, and C1 before because they do not affect the mass balance. They do affect the energy balance, but before we can do the energy balance, we need the temperature pressure. And we have the previous conditions that we talked about. And so now we put the temperature pressures everywhere. And based on this, we can now do the calculations. So that would be, but it is not finished yet. We can do the simple model and do the calculations. But after that, in order to do the rigorous process simulation, we would need to know the distillation design, number of stages, feed location, so on, compressor exit pressure, heat exchanger exit temperature. The conversion and stoichiometric coefficients are there already, so that part we don't need to add anymore. So if we use the simple model, then what you see in blue, the dark blue, like S1 and S2, we have specified the row of pressures in blue we have specified based on the previous mass balance, that is green. We have calculated the X that you see in red, that is the temperature. Okay, so this was using the mass balance and the composition and the pressures we calculated, and previous calculation of the compositions, we calculate, the red temperatures. And once we have got the temperatures, we calculate the enthalpy and find out which utilities, which unit operations need energy, which unit operations do not need energy. So that's the concept of doing step by step and finding out, rather than trial and error, giving temperature, pressure, and seeing what happens. We don't do that. We directly do the calculations without any iterations. I will skip this because this will be discussed in the next lecture. So now let's go to the problem definitions. Because we are solving different types of problems, all of them with the simulation, all of them with the model. So it is a good idea to know what kind of problem we are solving. The way we see it is that there is a flow sheeting problem, which is also called simulation. And the other three problems, like design, which also can be called specification, design, which also can be optimization, and design together with synthesis that we saw yesterday with very basic design. All of these can be solved with the simulation as an inner loop. So that's why we need to identify which is the simulation problem, which is the design problem, which is the synthesis problem. So let's see, if we look at the flow sheet and the arrows, the simulation problem is very simple to define. If we have all the information of the arrows going into the box of flow sheet, and what we actually calculate are what is going out, that is a typical simulation problem. So given all the incoming information, calculate what is going out and any internal variable. So simulation is the act of representing some aspect of the real world by numbers or symbols, which may be manipulated to facilitate any study. So remember, for simulation, we have all the information of the incoming streams, whether it is material or information stream, and we want to calculate what is going out. So that's the typical flow sheeting or simulation problem. And Just as an example, you can think of, just look at the distillation column. If you look at all the green variables, they are coming in, and what we want to calculate are the red variables. And then if we want to do a simulation, we can think of it that this is how the simulation would be done, even though we have a simulator that helps us to set up the problem, but this is how even the simulator would be setting up the problem. We define the problem. Always we need to define the problem in terms of chemicals, in terms of other things that is related to the problem that we want to solve. So after we define the problem, we need a model to represent our problem. If it is a chemical plant flow sheet, then we need a model for that chemical plant. And that model can be steady state or dynamic, depending on the problem we want to solve. So the model, one has to be careful. That can be a simple model, that can be a steady state model, that can be a dynamic model, that can be a 3D model. So depending on the problem we want to solve, the model will be different. Then based on the problem and the model and the analysis of the equations, as you saw with the incidence matrix and variable analysis, we need to find out what are the degrees of freedom, and those variables need to be specified. So we need additional collection of data. If parameters are missing, we need to know the parameters. Equipment parameter is missing, we need to give the equipment parameter, and so on. Once all the degrees of freedom have been satisfied, we are ready to solve the equation. Once we have numerically solved the equation, then we analyze the result. Just getting the solution of the numerical problem doesn't mean that we have a solution. One has to check the solution, whether it is correct or not. There can be errors that could be as a result of wrong data, that can be as a result of wrong choice of model. So even if the simulator says converge, does not mean the problem is solved correctly. So as the process engineer who is doing the simulation, they're responsible for the result. It's not the simulator, because they are solving the problem. It should be analyzed and checked whether the solution is correct or not. So with this, let's go to the next problem, the design problem. So now you can see that in the design problem, usually we know the input, we know some of the output, we do not know some of the operating conditions or some of the equipment parameters. So these are the design variables we need to specify or we need to decide on. So that's why the flow sheeting problem is that we know everything, we just calculate the output. But in this case, for example, we know the input and we know the product purity and the product we want. But we do not know the number of stages of the distillation column and feed location and so on. But we know the operating conditions. So it's if we want to solve with the simulator, it's an iterative procedure to solve it. We can also use the reverse design approach that Professor Mario Eden will talk about after me, and he will show you how without iterations, those equipment parameters can be found. And again, here is an example. So if we use the distillation example, so again, what is given are the green variables except L0 by D, that is initial estimate. But what we specify is XD and XB. And even though it is shown as a vector, it is actually one variable at the top, one variable at the bottom. And then we calculate everything else. So here we are interested in the design that gives us exactly the product we want. So we can do it in the simulation mode. So yesterday I talked about it already. It's a trial and error approach. where the unknown design variables, we assume a value, we solve the simulation problem, and then if our desired product compositions are not satisfied, we repeat. In order to help adjust the variables for optimization, the design variables, we can use an optimizer, we can use other techniques to accelerate the convergence. But it is still a trial and error. It would be, in the reverse approach, we do not need that trial and error. Then the optimization. The optimization is that we are not just interested in satisfying our specified output variables, specifications. We also want to minimize or maximize an objective function. So that's the only difference. So here also we add the additional information on the green. You see that we want the product purities as we have specified, and we want to have a design that will minimize the cost, at the same time satisfy our product specifications. So that's optimization. And again, you see that in the inner loop, we are doing the simulation. In the outer loop, we are adding the optimization. And optimization can be added both to obtain new estimates, but also to minimize the objective function. And depending on what other variables we want to include, if we want to include synthesis, like number of stages, feed location, things like that, then it will be not a NLP problem, but a MILP or MINLP problem. So now we can see that if it is optimization and it is, let's say, steady state design, we have the algebraic equations for our model. We collect the data. Then to solve the equations, we have the algebraic model, plus we need to put the constraints as well as the objective function. So together with the model equations, we have the additional equations, and that we want to solve through the optimizer. Here, we can do one thing, is that we can include all the model equations as equality constraints and simultaneously do the optimization and the simulation. So that would be the simultaneous solution of the optimization and simulation. The other way would be that we do the simulation, then in the inner loop, and we do the optimization in the outer loop. So based on this one, now let's see, in the online system, it's difficult to ask questions and get your answers. So we will do it differently. So let's say that we consider in the first example that we have a benzene feed and a hydrogen feed with methane as impurity. We know that benzene and hydrogen reacts to give cyclohexane, and the reaction takes place in the vapor phase, and there is 99.9% conversion of benzene. And the reactor operates at 497 degrees Kelvin and slightly higher pressure. We would like to obtain pure cyclohexane. So you see the questions there: which simulation-based problem do we have? Which phase equilibrium model to use? What type of model? Which method of solution we have to employ? So afterwards you can think about it, but actually this is the synthesis design problem, because we do not have a flow sheet. And because we do not have a flow sheet, it is the synthesis problem. If we want to do the mass and energy balance to optimize the cost, then we need a phase equilibrium model. And because it's hydrocarbons, an equation of state would be fine. And because we are doing steady state, so the model needs to be algebraic equations. It can be simple, it can be more complex, but it will be an algebraic equation model. The method of solution, if we want to optimize, we can do inner loop, outer loop, or we can do simultaneous solution approach. Okay, so that's the answer to the questions. Now let's look at this problem. Everything else is the same as before. The only thing I've added is that I've already added that we need a mixer, a reactor, a separator, a divider, plus utilities, pumps, compressors. So we have a flow sheet already. So which problem is this? If you think about it, that is actually a design problem. That can be specification of the design problem. It can be optimization, but it is a design problem. And the next one, we see that what I'm saying is that we already know the flow sheet. We already know the equipment parameters, all the input information. And if we have that, obviously the problem is a simulation problem. Okay, so you can see that the synthesis problem is the one where we do not know much and we have to generate all the data. The design problem is that part of the information is there, especially with respect to flow sheet, and everything else needs to be filled out. And in the simulation problem, everything has been done. We do the simulation. But the simulation has a purpose. The simulation will help us to identify or verify the design. Is the design good or not? We need to do the analysis, but in order to do the analysis, we need all the stream variable values. So let's look at now the steps and the tasks needed to go from, remember from yesterday, synthesis, so task 4 to task 9 that we want to do. And I will show you first graphically. So we have a flow sheet. We have already solved tasks 1, 2, 3. Now we want to find out whether our design is okay, and we want to analyze the design and verify the design. So we need to perform first a process design. We can do it first by doing the simple balance and do the mass balance. For every equipment, we need to find out which parameters to specify, only for mass balance. So for the reactor, it's stoichiometric coefficients, and conversion for the separators, the separation factors. That's all. Based on that, we add temperature, pressure, and with that we get the enthalpies and also amount of energy that needs to be added and removed. And at the bottom, then with using all this information, we have to find out all the equipment parameters that are needed for rigorous simulation. So based on that, we can see that in the first case, with the simple model, we just need the stoichiometric coefficients, the conversion factor, and the separation factor. Then in the middle case, having all those variables, we need to add the temperature, pressure, and the enthalpy. And then having all of these, we need to, for each equipment, we need to find out the number of stages, feed location, reactor information, exit pressure, and so on. Heat exchanger temperatures, and so on. And then once we have that, we can do the rigorous simulation. So up to now, you can see that in order to rigorous simulation, we need to have done a lot of design decisions. And the objective is not to have too many iterations so that we can directly go to the very good solution. So, but simulation is not enough. We have performed the rigorous simulation. The next step is the analysis. All the results that we have got from the rigorous simulation, we need to use those additional parameters like cost and so on. So we can do the economics, the sustainability, the life cycle assessment, safety. And after that, using all of this, we can say whether the process can be further improved and set targets for improvement. And if we are able to match those targets, then by definition, we have a more sustainable design. So task 4, therefore, is to do just the simple mass balance based on the flow sheet we have got from task 3. Tasks 5 and 6 is to set the temperature, pressures, and based on them, do the mass and energy balance with the simple model. Task 7 is first to provide the detailed specifications for the rigorous simulation, and at the same time, do the rigorous simulation. And then using the results from task 7, we use the results for doing the analysis in terms of economics and so on. And based on that, we do the final evaluation of the design in terms of targets. So these are the different tasks that we need to do in the design stage. And the methods and tools to be used for them. For tasks 4, 5, and 6, we use design methods based on simple models for mass balance. Use of thermodynamics is needed only for steps 5 and 6, tasks 5 and 6. Then we have the rigorous model-based process simulation. Before that, we need to specify all the model parameters that are needed. Then we need to do the equipment sizing and costing. And then we need to do the economic analysis. Now, if you're doing it iterative way, if you make a mistake already in the first task 4, afterwards you have to go back and find out that when you're doing the economic evaluation or equipment sizing and costing, some variable looks very strange. It could be that I've seen when I was teaching design course, students were coming with a heat exchanger length of 1 kilometer or a reactor the size of a football stadium. So why these values come? Because some design decisions have been made in task 4 or 3 that are not very consistent. So better design decisions means less iterations when you come here. And so in order to do this, what kind of tools can we use? So for the design methods, you see already ProCFD. It can help you with many of the design decisions. Properties are needed. If properties are not available in the database, we have property models to calculate the properties. Then for the rigorous simulation, we need a simulator. Then for the sizing costing, we need models for sizing costing. And then for other analysis, we need models for LC-soft sustainability and so on. So one thing you can notice is that if you have the simulator, it is only doing one task, simulation. So we probably are too dependent on the simulator, and we are using trial and error to solve the problems instead of having more dedicated methods that can help us to avoid the trial and error. So a little bit about the role of properties and property models. This will be in webinar 2 on 27 July, but because we need the properties, so I will very quickly go through it. What you can see in this table is that whether we are doing synthesis, design, control, energy analysis, environmental impact, economy, all of them, the properties affect all of those design decisions, or all of those decisions we make in synthesis, design, control, and so on. And why is that? Because the temperature pressure composition affects the phase equilibrium, affects the enthalpy, affects the density, the PVT properties, and so on. So if we are interested in the volume, the density is very important. Temperature pressure composition will affect that. If we are doing synthesis, the phase equilibria is very important. Design, the phase equilibria is very important, and how those properties change with temperature pressure composition. A single property value is not enough. We also need to see how the properties change when we change temperature pressure composition. And these are the variables that we can measure and we can specify. So it's very important to understand what is the role of properties and what they do in terms of the different problems we want to solve. So let's see try to define a property prediction problem. We have the molecular details of a chemical, single chemical or a mixture. What we want to know is the behavior of this chemical or mixture under certain conditions. And those conditions are conditions of temperature, pressure, composition that we will have in the process. So it's not just one property value, it is a set of property values at different conditions we need to know. How do we get it? If we have a very, very large database with all properties at all conditions of temperature, pressure, composition, we could use a database, but that's never a possibility. So we need to calculate the property, and then we need to choose the right model. And so the design synthesis, all this is a model and database. We need some data, we need a model to fill out the missing data. So what kind of properties we need, and we specify them or classify them as single value property. And these are like critical temperature, critical pressure, normal boiling point, normal melting point, heat of vaporization at boiling point, and so on. The important thing about these properties is that every chemical has one unique value. So if you know the molecular structure, they can be directly used to calculate this property, because molecular structure, a unique molecular structure gives a unique single property value. Then functional properties, properties that can change with temperature, pressure. So vapor pressure, heat of vaporization, density, they will change with temperature, pressure. So they, for any chemical compound, they are not a unique single value. Functional properties as mixture. We had the one above as pure compound, but we can also have mixture. So if we have a mixture, what is the mixture density? What is the mixture bubble point? What is the mixture dew point, and so on. And the last one are the phase equilibrium properties. We have a mixture. What is the XY diagram, vapor liquid diagram, or solid liquid diagram, or liquid liquid diagram for this kind of mixtures? So we have, as you can see, 4 different kinds of properties. We need all those in any complete process synthesis design analysis. The interesting thing is that the first 3, the primary, the functional, pure, and mixture, they are needed for the 4th one. So one has to remember that all these properties will affect our design decisions. And the way, if we want to do the phase equilibrium calculations, there are different ways to do it. You can use the equation of state, or you can use activity coefficient model, which is known as a Gibbs energy model, or we can have a combination of equation of state, Gibbs energy. So there are different options. And again, one has to make the right decision to choose the right model. Finally, I will show you, just as an example, what you see in the figure is a ternary diagram for solid liquid equilibrium. And the curve that you see are the saturation curve. If we want to do this, what is involved? So first, we need to know the compounds involved. So there is a solvent, there is a solid. We need to know the structure of those compounds. If it is 2 solids, then we have a ternary diagram. If it is 1 solid, we have a binary diagram. So the first, let's say, single property value we need are the heat of formation or heat of fusion and the melting point. So every molecule has a unique value. We need to know that. If we have that and we assume ideal, then we can just make a straight line and get the saturation curve. But if we want to calculate the points on the curve, then we need a model to calculate the activity coefficient. And to calculate the activity coefficient, we have different options. If we have all the parameters for the activity coefficient, or even the activity coefficient in a database, we can directly take them, and we have for every point the values. But if we need to calculate for every point the parameters, then we need all these extra things. we need data. We need to feed the data to the model parameters. And once we do that, then we solve for the solid liquid equilibrium conditions. And all those things you will see in the next lecture. What are the equations that we need to solve? Because there are some equilibrium conditions that need to be satisfied also. So with that, we can summarize that the preliminary tasks in stage 2 requires quick setup of mass and energy balance with simple models. From the mass balance, properties are not needed, but they are indirectly used to make the design decisions. So for example, when we set up the mass balance with respect to stream calculators, we need the separation factors. If we have some phase equilibrium information, we can easily make those decide the separation factors. Or if we know that the system has an isotropes, then we cannot directly say that this separation factor can be used, and we would need a solvent and so on. So information about the system can help us to make those design decisions. And then once we have finished the mass balance, then we need to add the temperature pressure so that we can find out the state of the chemicals in every stream and calculate the enthalpy. Remember that the vapor enthalpy is quite different from the liquid enthalpy. And so if the state is wrong, then the enthalpies will be wrong and the calculation will be wrong. So we need property models that need to be consistent and correct, because if we use the wrong property model, we may not find the isotope, we may get wrong enthalpies, and so the design will be wrong. And simulation is a tool that verifies the design decisions. It provides the data for analysis, but it does not do the design. It generates the data that we need so that we can define targets for innovation or improvement. So these are the things. The next lecture by Professor Eden will start from here and say all those design decisions that we need to make for every equipment, how do we do that? And we are going to use the reverse approach, meaning that if we know what is coming in and if we know what is going out, and we have some information about the chemical system, we can directly say what should be the feed location, and what feed location for a given number of stages will give us the product. And that can be said also from the point of view of energy, because that will be the minimum energy required for that distillation. So although we will not say that we have the optimal flow sheet, it will be very close to optimal with respect to energy requirements. So those things we will see in Professor Eden's lecture. And then I will come back and finish that if we have the simulations and all the stream information, how do we do the analysis? And based on the analysis, how do we set the targets for improvement? And also the demonstrations will highlight all of these things. So I will stop here and let's see if there are any questions.
If anyone have any questions, you can raise hand.
Or put any question in the chat. Okay, looks like I was very,
No, there's no any questions in the chat now.
So it looks like I was very clear, or I was not at all clear. We will see afterwards. And Maybe I can ask some question and you people can, one of you can answer. So do you come across in your design that you have to redo the design because the heat exchanger is very big or the column dimensions are very big or very small? Who can comment on that? I see that Zulfan Adiputra has said yes. Do you want to unmute him so that he can comment? The organizers, can you unmute Dr. Zulfan Adiputra?
Yes.
Number 12.
Yes, we have unmute already.
Okay, do you want to say anything? Okay, it looks like we cannot hear him, or he has answered its typical question. How do we make sure if thermodynamic model that we select is correct? So that is a big problem. I would say people with more experience can make better decision, but what we are trying to do is to provide sufficient information so that one can make those decisions very clearly. So how can we check whether the thermodynamic model selected is correct or not? Well, typically, it would be a good idea that if you are doing a separation and the two key compounds, you know, maybe you can check the vapor-liquid equilibrium or measure those vapor-liquid equilibrium against the model you have. So that would be always a very important issue. If you have multi-component mixture and some compound is mutually soluble, so that is again another thing to check whether the thermodynamic model gives the mutual solubility. So what is the solubility there? And another issue was with limited experimental data or field data, how do we check this? The important thing is design of experiments. People don't talk about it very much, but it is a very important issue that if one does a design of experiment to find out what are the minimum number of variables for which I can do a design, measure those variables, and then check through my simulator whether those variable values have been satisfied or not. So it is not necessary to arbitrarily do all kinds of experiments and measure the data, but do a design of experiment and carefully identify which are the most important variables. So for a reactor or some other equipment where the volume is important, the density is very important. And do we have the density correctly? For the heat exchangers where heat transfer is important, the heat transfer coefficient is very important. For distillation, of course, the vapor-liquid equilibrium. For crystallization, the solid-liquid equilibrium. Also for calculating the heat duties, the heat of vaporization. Sometimes only one data point is enough to verify the design or to verify the simulation. But it is a good idea to find the sensitive variables and then do the design. Now, I also mentioned that during my presentation that you can get a heat exchanger 1 kilometer length long or a reactor with a volume that is bigger than a football stadium. Why is that? There could be several reasons. One could be the residence time taken, because the residence time and the feed flow rate into the reactor will affect the volume together with density. So if one has taken a high residence time, it could be a problem. Or if the production rate, the capacity, has been chosen to be very large. Because if we look at the demand for a chemical, it doesn't mean one chemical plant will satisfy the demand for the whole world. Sometimes that is a typical mistake that will give a very large flow rate and therefore very large equipment. And sometimes it is the opposite. It is so small that you can put the plant or the reactor in your table, or even a drawer in your table. That is because the flow rates are too small and maybe the residence time is too short. So there are different reasons for that. I can see a question. Can we perform simultaneous optimization and simulation for large scale, nonlinear dynamic systems? Yes, we can, depending on the problem. I would say that many of the process synthesis problem that Professor Grossman discussed yesterday with respect to heat integration, these are large problems and they can be solved simultaneous synthesis and optimization. We will have some example also tomorrow where you will see the entire flow sheet is taken together with the heat integration and simultaneously solved. Also in the process synthesis step superstructure optimization, those ones we have solved for more than 1 million equations. So yes, these are possible, but the more nonlinear they become, the more difficult they are. And I would not suggest to solve all the equations simultaneously. It could be possible to break down the problems into sub-problems and then use simultaneous optimization and simulation to solve each of the sub-problems. Any more questions? Yes, somebody said also the minimum approach temperature. That maybe the simulator will already flag this if the heating curve and the cooling curve cross each other because of the minimum approach temperature, then it will already be told. But yes, simulators can break down because of that. Anything else? If you have more questions, we can always take them afterwards. So now, in order not to keep Professor Mario Eden waiting, I will stop here and the Thai office hosts will allow him to get in.